So we're going to look at sampling and sampling distributions. When we're dealing with sampling, we're basically preparing you for research. So you need to understand that a sample emanates from a population. And the population is the entire when you're looking at the population, we're looking at the entire sampling frame from which the samples emanate. So a sample is simply a component of a big population. So to understand and appreciate sampling, you must identify the types of sampling techniques that are there. So in your own understanding, why is it important to sample? Why is it important to sample? Why is sampling important? If we can go for the entire population, and the population is more accurate than a sample. Okay.
It's time consuming and costly. Taking a sample than a population, because the sample you're taking just a part of the population. You're just getting a chunk of the population size.
And the others? Okay. So that's true. Sampling takes a lot of time. So we can define sampling in many terms. So I can simply say sampling is simply the process of selecting Sampling is simply the process of selecting a subset of individuals or items from a larger population in order to make an estimate, approximation of the entire population. So in statistical terms, we can simply say sampling simply is a selection of a subset of observations from a population, which allows us to make inferences about the total population based on the characteristics. So sampling can be done using different methods. There's what we call a simple random sampling. There's what we call stratified sampling. There's what we call cluster sampling, convenience sampling. Now, the method that you need to choose when you're sampling depends on the research questions and the characteristics. So now we need to understand in details what each of these are. So sampling is very important in research, and it's also important for data analysis because it allows us to draw populations, to draw conclusions about populations using smaller samples. All right. So questions will come, define these different types of sampling methods. Now I can say that these sampling methods can be subdivided into two. There's what we call probability sampling methods and the non-probability sampling methods. Okay. Are you together so far?
Yes.
So when we're dealing with probability sampling methods, we're dealing with things that have to do with numbers. So each of these types has an example that you need to know under each of them. So I'll explain all of them in depth. Like I said in the preamble, to say your course is 30% theory and 70% quantitative. So you can't run away but understand each of these components. So please don't think I'm eating a lot of your time by explaining these. Are very important. So when we are dealing with I hope you're able to see my screen very clearly. Okay. So when you're dealing with is the screen clear? Is there any black thing on top, or it's not appearing?
No, it's clear.
Okay, so I was saying there are two types of sampling methods. There's what we call probability and non-probability method. So when we're dealing with probability sampling, we're looking at a process that involves selecting a sample in a way that each member has equal chance of being selected. So the probability that is being considered as a standard method that negates biasness. It allows each sample to have an equal chance. So under probability sampling methods, we have several. Number one, we have what we call the simple random sampling method, where each member is given equal chance of being selected. For instance, you want to select candidates in a class to represent, you just want to select randomly, you pick them up. Or if you want to see the impact of COVID, you just go to randomly select people and test them to see whether there is COVID around. Okay. Then when we are dealing with stratified sampling, we're looking at a population that will be divided into subgroups, and a random sample is taken from each subgroup. So you stratify them, for instance, top, middle, and low management. So you pick 3 from top, 3 from middle, 3 from, so those subgroups are called strata. We also have what we call systematic sampling method, where the members of the population are selected at a regular nth interval. For instance, every 10th, like we do tithing, that's systematic benevolence, where we get to randomly give God the 10th. If you have 100 cattle, every 10th is selected. If you are also picking customers, every 9th customer, you pick them. So that is another sampling method you could choose to use. We also have what is called cluster sampling, where the population will be divided into clusters, and the random sample of the clusters is selected, then the members are selected from the clusters and are included. For instance, you get a cluster of Tongas, a cluster of Bembas, a cluster of Tumbukas from the different provinces that we can, in this case, call the clusters. All right, so that is under the probability sampling method. Are we together? Are we following? Are we moving together? And then we now go to what we call the non-probability sampling method. Non-probability sampling method. And in non-probability sampling methods, we do not involve numbers. We are not even concerned about being biased. We are just looking at what is feasible and practical. For instance, we have what we call convenience sampling method, where you are going to select your respondents based on availability or willingness to participate. Or conveniently, because you're based in Lusaka, you want to select your workplace. We have snowball sampling, which is a sampling method which works so much on referrals. Like a snow grows into a big ball, one who knows what it's usually used in investigations or referrals. For instance, you're doing village banking. You use a group that knows who is in the members and how many groups are there doing village banking. There's quota sampling, where the population is divided into subgroups and the specific number of participants is selected from the subgroups. For instance, you're looking at babies, teenagers, adults. So these subgroups were selecting based on a particular characteristic. Then purposive, which is also called judgment-based sampling, is one where you're going to use a specific criteria to select your respondents. For instance, age or gender or intelligence. For instance, you know that not everyone can represent a class. when it comes to debate, you look at people who are vocal. So you purposively select them. Sometimes you are purposively selecting people who would want to give you an experience of circumcision, whether circumcision affects the sexuality of an individual. You can't pick people who have not undertaken circumcision. So you purposively sample those who have had an experience, or you want to understand how COVID affects. So you only get people with testimonies. So you purposively sample them. So it is important to understand that probability sampling methods will give you a practical and accurate result based on the method you choose to appropriate in a particular instance. You don't choose any randomly. You can also use a mixture of both. For instance, you use both convenience sampling because you are working for Zanaco Bank and simple random because you want to negate biasness. So these are the sampling methods that we use. Are we together so far?
Yes.
So now, we now still go back to the question, why is sampling important? Why is sampling important? Why do we sample? I talked about a number of reasons. Number one has already been mentioned, do with cost implications. So sampling is important for several reasons. Number one, may not have enough funds to research on the entire population. And moreover, it may be time consuming and expensive. So sampling allows the researchers to gather information from smaller subsets. After all, it will save your time and resource. Feasibility. Sometimes, no matter how much time you have, it is impossible to collect data from the entire population. So in these cases, a sample will just be a representation, which will yield useful insight. Accuracy. Sampling can also provide an accurate estimate of the characteristics of the population at hand, which would be effectively representative. Generalization. If a sample is representative, the results can be generalized to the entire population. It is sufficient to make decisions and predictions. So you can tell to say, if we are able to tell that one member of the house has COVID, most likely it would spread to the other. So you do a test on each one of them. You can generalize that there's COVID in this home. Ethics. It is also important to be ethical when conducting research on the entire population. So sampling allows researchers to minimize the risk of what? So I'm a researcher. So certain times when students come and want me to fabricate data, which you guys sometimes would want me to. So ethically, I would want to actually relate the information to what is obtaining on the ground. So we'll do what is called pilot testing, so that we could peradventure understand what is obtaining, so that even as we generalize from the sample we're going to collect, it is close as much possible to the truth. Practicability. So in some cases, it may not be practical to collect data from the entire population, no matter how much funds you have, and therefore sampling is the only way out. You can't know how many babies are born. Somebody's born somewhere without documentation. So you just get to generalize. Are we together at this point?
Yes.
Any questions, please, you could ask. So that we can move. All right, so now let's go to the formulas, the quantitative part of sampling. So I'm going to take you through formulas. So we're going to deal with a sample and a proportion. Okay, so n stands for a sample. It's given by z squared, s squared over e squared. All right, the z is a z-score. The s squared is a variance. Then meaning the s is simply standard deviation. And e is what? Error term or level of precision. Then we also have the p, the proportion, and our q is a failure, and minus p is a q. So we have two formulas, z squared pq over e. Under confidence interval, we also have four formulas for one sample. Our confidence interval is equal to the mean plus minus z standard deviation over square root of n. At b, for a proportion, a sample is equal to what? Proportion plus minus z p over q square root of n. N, in this case, square root everything. So we are not given the proportion. It's a small sample over a big sample. All right. So Z is only used when samples are greater than 30. When samples are less than 30, we use a T. There's a table which we call the T table. So in that case, our confidence interval for samples less than 30 will be given by same mean plus minus T standard deviation over square root of n. So this is for single samples, and estimation is always under two-tailed. And so we have a song that we need to learn, where we need to understand that the confidence level are numbers more than 50. We have what? 99, 98, 95, and 90. These are common confidence levels. These are the common confidence levels. So what is the confidence level and what is the significance level? So the difference from 100 is called significance level. The decimal point of significance level is called alpha. And the Z, which is the two-tailed. So here we have 1%, the difference from 100, 2%, we have 5%, we have 10%. When divide this by 100, we have 0.01. Divide this by 100, 0.02, 0.05, and 0.10. So the Z for this one is called 2.58. This is 2.33. This is 1.96. And this is 1.645. So these are the songs that we'll be learning. Okay. So what is a confidence level? What is a significance level? So you find these terms over and over. So these ones are parameters that we're going to use that will help us determine our levels of confidence when you're dealing with estimation and when you're dealing with hypothesis testing.
Sorry, Collins, I've got a question.
By definition, I can define them as follows.
Collins, I've got a question.
I'll allow you to ask. Let me just finish. So when I ask it to define what confidence level is, so confidence level is simply the degree of certainty with which we can estimate a population parameter based on a sample. Significance level, which is also called alpha, is the probability of rejecting the null hypothesis when it's actually true. So the difference from 100 is the significance level. So confidence level is a degree of certainty. So we came up with these figures here. 99, which is 1%. 90, which is 2%. 98 is same as 5%. And 90 is same as 10%. When you divide this by 100, we get 0.01, 0.02, 5, 0.05, 10, 0.10. Now, how do we get these figures? Do we just memorize them? There's a way to find them. Yes, you can memorize them. There's also a way to find them. So for instance, 95%, which is 1.96. So we take ourselves to the tables, Z tables. So we remember how to read the Z tables to start with. If we're reading, for instance, 1.23. How do we read 1.23? We go under 1.2 here, and the 3 will be 0.03 here. Where they meet, the reading is what? 0.8907. So this is a Z, and that is the probability. But if I asked you this probability, 0.8907, what is the Z for this one? You just add the figure there, 1.2 and 0.03. So it will give me a Z of 1.23. Suppose I asked you to give me a Z of 0.9750. What number is there? 1.96. The number is there, 0.06, 1.9 and 0.06. So this one collectively gives me 1.96. Now sometimes you'll be asked to find a probability of a figure that is not there exactly. You pick the closest possible. For instance, 0.90800. So when you go here, 9800, somebody may think it is this one, the other one will think it is this one. So you pick the closest possible. This one is below by 2 points. This one is above by 2 points. So you pick this one here. So this is 2.05. Now, there are instances where you'll be asked to find figures that are a little bit equidistant, like 0.9500. So this one here, you discover that somebody may pick this one. It is above by 5 points. Somebody may pick this one, it is below by 5 points. And which one is closer? The examiner can choose any of them. But the most accurate is the figure in between these ones. So we start with the smaller one. So 1.64. Then you add a 5 at the end, meaning there's a becomes 1.645. 1.645. If it was between 1.67 and 8, you start with the smaller one, or 1.675 at the end. Because 0.05 means in between. So you need to understand where that is coming from. So in this case, where we're being asked, how did we get this 1.96%, 1.96 as I said. So the method of reading those ones simply 1 minus alpha over 2. So if you have 95%, well, let me say 95%. So our alpha here, so we know this is 5%, meaning the alpha is 0.05. So using this method here, we're going to have 1 minus 0.05 divided by 2. This will give us final answer, which is 0.975. So we check for the 975, this is a probability. What is the Z for this probability? You go into the table here, 0.975, which we already found here, which is what? 1.96. That is where the 1.96 is coming from. Now, it's very important to know this method because sometimes the examiners will give you a percentage like 97%. So it is not part of our sum. What we do? 1 minus alpha over 2. So here we know it's 3%, the significance level, meaning here we have 0.03. So this will be 1 minus 0.03 divided by 2. So 1 minus, use BODMAS because sometimes people will do everything correct but misled because they're using what? They're abusing the calculator. So when you subtract 1 minus 0.015, it will give you 0.985. Since we can add a 0, since we get 4 numbers like there. So we go into the table, 9850. So 9850, go into the table. Can somebody help me to identify 9850, 0.9850? It's zoom and screen. Zoom and screen. What are you finding closest? 2.17, is that closest? .17, is that the closest?
Exactly 2.17.
2.17, eh? Yes, so 97% will be 2.17. Hence our song. Let's go back to our song now. So this song is an anthem that will help you understand where the figures are coming from. So the song was composed by me. So let's go through our song. Just give me the Z figures. All right. So what is the Z for 99? 2.58. Okay, what is the Z for 98?
2.33.
2.33. The Z for 97?
1.96.
Try again. Software on the screen.
2.17.
2.17. 95?
1.9.
90?
1.645.
0.645. 80%? We calculate, we don't have it. All right. So 80%, we don't have it. Any questions so far? There was a hand now. I can allow you to ask.
No, it has been answered. Thank you.
All right. So you see, it's important to wait for me to finish up, isn't it? Okay, so we can now go to some of the questions that would be of interest. So we've talked about the two formulas. let's the questions you'll have: define sampling error and the types of sampling. Give an example of each. So tell me the type of sampling and give me examples of each quickly.
Cluster sample.
Probability sampling and non-probability sampling.
So generally we have probability and non-probability sampling methods. Yes, so under probability method, which examples have we talked about? Under probability we have what? We have already
Simple
presented
random
what?
sample.
Yes, the simple random sampling, yes, number one. Number two,
Stratified random.
the stratified sampling method, yes.
Systematic and cluster sampling.
Systematic and cluster sampling. All right. Then under non-probability sampling method, what do we have?
Convenience.
Convenience, yes.
Convenience. Snowball sampling.
Snowball sampling.
Is it quarter? You said quarter? Quarter sampling.
Quarter sampling. You guys are not bad after all, eh? That's good. Usually, the BIDs from each intake supersede the other intake in being BID. But this one is defying the narrative. You're supposed to be worse than the previous BID group, but you're not as bad.
Sorry, Mr. Collins, what was the question? I didn't get it.
So first the question is what is sampling error? Difference between, so sampling error is the difference between the sample statistics and the true population parameter. So sampling error is inevitable in any sampling process because a sample can never perfectly represent the entire population. However, sampling error can be minimized using appropriate sampling methods and increasing the sample size. So there are two main sampling methods that we're going to look at: probability and non-probability. So under probability, we talked about these methods that include selecting a sample from a population by a way in which a member of the population has equal chance. So you've given me the examples, like simple random, where members are selected from the group by way of drawing them out of them. For instance, the marbles, you can shake them and randomly collect them, or a lotto. We also looked at stratified sampling method, which looks at dividing population into subgroups based on the relevant characteristics. Okay, for example, dividing a group into age and selecting from each of them. You also took me down to stratified sampling method, which includes what? Selecting the nth individual from the population. For instance, the 10th person on the list of names, or cluster sampling, where we divide what? The groups into clusters. All right. I think I labored hard to explain that in the
Sorry,
best
Mr.
possible
Collins,
manner.
just a question here.
Yes, please.
So it's like cluster sampling and stratified sampling, the difference is quite minimal
Yes.
in that in stratified sampling, after you come up with stratas, and then from those stratas, you again pick the samples from those stratas, isn't it?
Yes, you subdivide them into the subgroup, which we call strata. Then these are based on some relevant characteristics. Then from those strata, you randomly select the individuals from each subgroup. For instance, the population could have age, you pick 10 from that age. Population can have gender, you pick 5 from that gender. So each of these groups have a similar characteristic, then you select from them. And where we go to the cluster, you divide the population into clusters, like neighborhoods. For these people who came from this school, then randomly select the clusters, including the sample. So you pick the whole cluster as a group to say, okay, the schools, we've picked 5. The neighborhoods, we've picked the cities, we pick them smaller. Yeah, the similar procedure. Then we go to non-probability sampling, which does not involve random selection, like convenience sampling, where you select individuals because of easy access or readily availability. For instance, if you are conducting a survey on your street. Snowball, where you're selecting individuals based on referrals from other participants. For example, you are making referrals to join what? Let's Chat. So this is person who has Let's Chat is going to call somebody and they will join based on a referral, and a bonus is given to a referral. We also have quota sampling, where you are looking at selecting individuals who meet predetermined quotas based on some relevant characteristic. For instance, age limit from under 20. It's a quota sampling of a team. If you're above 20, you now go to the senior team. So you need to meet a characteristic. This one is specific for a particular gender. It has nothing to do with numbers. Purposive sampling, you're basing individuals on a specific criteria: intelligence, IQ, gender, expertise, all right? Had COVID before and experience. And examples of sampling error. If a study is conducted using simple random sampling, we estimate the percentage of adults, for instance, in a city of Lusaka, who support a certain political party. So the sample may include more or fewer supporters than the actual population. So the difference between the sample statistic and the true parameter is what we call sampling error. So because we looked at what? A stronghold of PF, for instance, or a stronghold of UPND, when you go to select their responses based on which political party they love, obviously they'll say UPND. But if you're going to get a representation, it is the entire country that gives the true figures. So that's what we call sampling error. Difference between the sample statistic and the true population parameter. So if a study uses convenience sampling methods, for instance, to survey at UNILAS about students and how their study habits are, the sample may not be representative of all colleges, because maybe school is tough at UNILAS and it is at NIPA. So if you're going to generalize to say all students in colleges study, so the difference between you conveniently sampling a school because you're coming from there, you need to use what parameters that will justify the same levels. For instance, use CBU or UNILAS and ZCAS, for instance. Even as we are looking at countries in Southern Africa, you cannot compare certain countries to South Africa, even if they're in Southern Africa. So that's what we call sampling errors. They emanate from justifiable differences. And these sampling errors are errors that actually we make in marriages, where we want to compare how I relate with my wife and how I tolerate certain nonsense that my husband does because the other couple behave like this. That's sampling error. Maybe they have different social backgrounds. So compare yourself to somebody who is of your same level. So I hope I'm making it clear in the errors that are actually made when you're doing sampling. All right. So I have taught you a song and I have taught you some formulas. And these formulas, I need you to recite them for me. N is given by what?
Z squared multiplied by S squared divided by E squared.
Or
Z squared PQ over the B squared.
all right, confidence interval given by
X bar
Z score.
over the square root of
or over n. All right. So let's look at this question. Number 2. Okay, he loves these questions so much. So I need you to understand them so that you're ahead of class and understand. All right, so suppose a random sample of customers has an average of 78 and a standard deviation of 22. Do a 90% confidence interval given a sample of 40. So what are we given here? 78 is what? X bar. Then 22.5 is our what? Standard deviation. So let's calculate a 90% confidence interval. So here we have 78.25 plus minus 1.65. And standard deviation is 22.5 over our sample size is what? Root of what? 40. Okay. Then they have changed part B, find a 90% confidence interval for a sample size of what? Over 75. So I want you to comment on the difference in the confidence interval. One is going to be constricted and one will be broader. So what does it tell you? When you increase the sample size, the accuracy level is higher. So for instance, if we had 40, 50, and we had 40, 60, which one is higher? And what could be your difference in the confidence interval and the explanation?
According to the question,
Uh-huh.
where did 1.65 come from?
Can somebody explain 1.65? Where is it coming from?
that's the Z value for 90%.
90%. That's
Is it
what
supposed to be 1.645?
it's the same thing. 1.64. The most accurate is 1.64.
You rounded it off.
So which is 1.64. So it's the same thing in his solutions. He used 1.65. That's why I'm using it, because this is what you're going to look at tomorrow as he'll be teaching you. All right, so it's the same thing.
So the key is to just identify what you've been given, then you know what formula to use, not so.
Yes. All right. Okay. Question number 3. What is the difference between a point estimate and a confidence interval? What's the difference between a point estimate the confidence interval. Anyone who wants to try? So we're dealing with a point estimate like a mean X bar or a standard deviation. All right. Point estimate is such a single value used to estimate a parameter. A confidence interval is a range of values within which you could estimate the true parameter of the population. So in short, confidence levels play a role in identifying the confidence interval or the range to measure the precision, whereas a point estimate just gives us what? The actual parameter of the population. So you need to understand that. All right. So I repeat, when we're dealing with what? A point estimate is simply a single value that is used to estimate an unknown population parameter such as a mean, a standard deviation. For example, a mean can be used to estimate a point estimate of a population. However, point estimates can be affected by sampling error and may not perfectly represent the true population. Confidence interval, on the other hand, is a range of values that are likely to contain the true population parameter based on the sample data. A confidence interval takes into account the sampling variability and therefore gives you a range of possible values within which a parameter is possible. And the width of the confidence interval depends on the sample size. So you need to understand that the variability of data and the confidence interval move together. So if you have a higher sample size, how is the confidence? So confidence level represents the degree of certainty as I talked about. And so we can estimate the parameter based on the sample. So what is the relationship therefore between the confidence interval and the sample size? Can somebody tell me the relationship between confidence interval and sample size? So this would guide you in understanding the next question that follows. So confidence interval values will likely contain the true proportion parameters. So if the sample size increases, the width of the confidence interval decreases. If the sample size is small, the range is big. So if somebody tells you that it takes 8 to 10 minutes to walk to school, and the other one tells you it takes about 5 to 15 minutes to walk to school, who do you think is more sure? The one with a constricted confidence interval. So you need to understand that for a higher sample size has more precision. So if your N is higher, the confidence interval will be more precise to be small. N is small, confidence interval will be bigger because you're not very precise. So as you increase on the sample size, the level of precision is higher. So in the case where we had sample size 40 and sample size 75, we just wanted you to identify the difference, the confidence interval. If here the confidence interval was 40 to 50, maybe when you increase the sample size, confidence interval will be 40 to 45. That's a lesson that I want you to pick from there. Is that clear? Right. So a sample size of 36 engineers has an average of 41.7 and a standard deviation of 69 years. We'll construct a 99 and a 95 confidence interval. So what do we have in the question? what we have in the question. Our n. What is our n? N is 36. What else are we given? X bar is what? 41.7. And standard deviation is what? 6.9. So calculate a 95% confidence interval. So in this case, we're going to have what? X bar plus minus Z alpha over 2. Standard deviation square root of n. This alpha over 2 is our song. Don't get confused. Don't divide anything by 2. Just get it. It's as good as just Z. So here 41.7. Then we have plus minus 1.96. Standard deviation is 6.9. And our n is what? 36 square root. All right. Am I confusing someone here? Are we moving together?
Yes.
And here,
Yes.
99% confidence interval. 99% confidence interval will simply be 41.7 plus what? 2.58.
2.58.
Correct. And here we have 6.9 root what? 36. So in the previous example, they were manipulating the sample sizes. Now here they're manipulating the confidence level. What happened when you increase the confidence level? The confidence interval. Is it more constricted or more precise? All right. So I adjure you to go through this tutorial sheet and answer all of them. I've taught everything here. I don't know which question would give you a tough time. All right. Find a 95% confidence interval for a proportion of 10% whose sample size is 50. So in this case, what are they looking for? Confidence interval for proportions. All right. So we're going to use formula 2. So formula 2, we're going to have what? What are we given in here? Z is what? 1.96. N is what? 50. P is what? 10%. Q is what? 90%. So what's the formula we're going to use? Confidence interval is equal to P plus minus Z PQ over root of N. So here is 0.1 plus minus 1.96 and then 0.1 times 0.9 over what? Over 50. All right. So if you answer here, I'm just assuming since you guys are lazy at calculating, if you had something like this, so this would be 0.08 to 0.12. So meaning it's between 8% and 12%. That is what? The interval. You can leave it in decimal point or in percentages form. Still correct. I repeat, this was just an arbitrary calculation. Just be letter sensitive so that you get correct figures for good interpretation. All right. Let's go to another question. A researcher wishes to estimate 99% confidence that the population of adults are confident about the country banking system. He estimates to be within 4%. The word within is the same as error. What is the minimum sample size needed to be available? What is the minimum sample size needed? Okay, so here they are looking for N. So whenever they're asking you what is sample size needed, they're looking for N. So in this question, what do we have? So the question is as follows. Researcher wishes to be 99% confident. What are we given? So Z here is what? Z is 2.58.
2.858.
All right, what else are we given? So researcher wishes to be 99% confident proportion of adults. He estimates that we must be within. The word within is error. So error is got what? 4%. What is the minimum sample size? All right. Needed for us, assuming there's no prior information. So if there's no prior information, we're assuming that what? P is 50% and Q is 50%. You need to negate biasness. So the sample size N is got what? Z squared PQ over what? E squared. So here we're going to have 2.58 squared times P is 0.5 and Q is 0.5. And error is what? 4%, 0.04. But the next one here, we've been told that we have prior information that 20%, 38% of the respondents have what? Confident. So 0.38 will be your P. In your Q should be what? 1 minus 0.38. All right. So here my people perished because of what? Lack of knowledge and not attending Collins's classes. So in this case, 0.62 is our Q. So to find our N, Z squared PQ over E squared. So our Z is the same from 99%, 2.58. What changes simply here is 0.38 and what? 0.62. So we end here. I'll ask for 2 or 3 questions.
Okay, just a clarification. So all the time when there's no prior information, you use 0.5 for both the
Yes.
P and the Q.
So whenever there's no prior information, we use 50-50. And whenever we have no confidence interval, the standard is what? 95%, which is 1.96. So if you have no confidence interval, confidence level, the standard is 95%. Thank you so much for that question. Any other question?
Sorry, I joined a bit late. The notes that you're giving, did you share this, or maybe we have to look at the previous notes you gave us? The definition of sampling and the other things.
Those are from my head.
Are you going to share this video later?
Yes, I'll share the video. I'm assuming all of you are in the paid up group. So I didn't share this with the outsiders.
In the office now.
All right. Okay, thank you
Uh,
so much.
Can you go back to the other question? I raised my hand area. The other example, not this one, before this one.
Okay, all these questions I've sent them on the group.
Excuse me?
These ones.
No, I'm asking for the other example that you did, the example before this one,
It
the
came
last one.
from here. All the examples came from here.
I'm asking you to go back to this page. I
Mhm.
wanted to ask, not this one, there was the one that is 450 and you're comparing, yes, this one. So now the calculation where your pencil is 0.10 plus 0.02. I wanted to understand how we have calculated to find the 0.08. What have we multiplied or what
So
have
we
we
start
done
with
there?
0.10 minus 0.02. That is the lower bound. And 0.10 plus 0.02. So if we subtract So 10% minus 2%, 8%. Then you add 10% plus 2% is 12%. Or 0.12, and you first subtract, then you add. That's what plus minus means. So if you had 20 plus minus 5, what does this mean? The interval will be what? 15, 25. It means you first subtract and you add. Is that clear?
That's great. Thank you.
All right. Thank you so much. Have a good night.